Now today we are going to start new topic, phase equilibria and phase rule. Now before initiating the discussion of phase equilibria and phase rule, it is important to define and explain certain terms which are used frequently in this connection. These terms are phase, component, and degree of freedom. Phase is defined as any homogeneous and physically distinct part of a system which is bounded by a surface and is mechanically separable from other parts of the system. A phase may be gaseous, liquid, or solid. It is perfectly homogeneous and distinct from every other phase that may be present in the system. There must be a definite boundary between two phases. This boundary is known as interphase. Since gases are completely miscible, a gaseous mixture, irrespective of the number of gases present, constitutes only a single phase. There can be no bounding surface between one gas and another. Thus, air, which is a mixture of nitrogen, oxygen, carbon dioxide, water vapor, etc., constitutes a single phase only. A system consisting of one phase only is said to be homogeneous. Two or more liquids completely miscible with one another also constitute a single phase, since there is no surface of separation between them. Thus, water, methyl alcohol and acetone, if present together, will exist in one liquid phase only. But as there will be vapors in contact with the solution, there will be two distinct phases in the system. A mixture of two immiscible liquids such as water and benzene will exist in two distinct liquid phases, and in addition there will be a vapor phase. Thus there will be three phases, each separated from the other by a well-defined bounding surface. Next terminology is components. The number of components of a system at equilibrium is defined as the smallest number of independent variable constituents by means of which the composition of each phase can be expressed by means of a chemical equation. Now if we see the system, sodium sulfate water system, the various phases that may exist are sodium sulfate, Na2SO4 7H2O, Na2SO4 10H2O, ice, solution, and vapor. It will be seen that the composition of each phase can be expressed in terms of sodium sulfate in water as shown in this picture. Now first, Na2SO4 components are Na2SO4 plus 0H2O, Na2SO4 7H2O components Na2SO4 plus 7H2O, Na2SO4 10H2O, components are Na2SO4 plus 10H2O, Na2SO4 solution, Na2SO4 plus XH2O, ice, 0 Na2SO4 plus H2O, and vapor, 0 Na2SO4 plus H2O. It is seen that the composition of some of the phases can be stated in terms of only one component, yet the composition of some other requires to be stated in terms of two independent components, namely Na2SO4 and H2O. Thus, two components is the smallest number by means of which the composition of each phase can be satisfactorily explained. Hence, it is a two-component system. Calcium carbonate on heating in a closed vessel exists in equilibrium with its decomposition products, calcium oxide and carbon dioxide. Calcium carbonate solid gives calcium oxide solid plus carbon dioxide gas. This equilibrium constitutes a system of another type, two solids and one gas. At first sight, it appears that it is a three component system, but as can be seen, these constituents are not independent of one another as required by the definition. For example, calcium carbonate is equal to calcium oxide plus carbon dioxide, calcium oxide is equal to calcium carbonate minus carbon dioxide, or carbon dioxide is equal to calcium carbonate minus calcium oxide. Thus, any two of these three substances can be chosen as independently variable constituents, hence it is a two-component system. The composition of each phase can be expressed in terms of any two of the constituents as shown below. As shown in this picture, we can see in this picture, if calcium oxide and carbon dioxide are chosen as two components, then phase calcium carbonate, composition calcium oxide plus carbon dioxide. A phase calcium oxide, composition calcium oxide plus 0 carbon dioxide. Phase carbon dioxide, then 0 calcium oxide plus carbon dioxide. If calcium carbonate and carbon dioxide are chosen as two components, then phase calcium carbonate, composition calcium carbonate plus 0 carbon dioxide. Calcium oxide phase is selected, then calcium carbonate minus carbon dioxide, composition carbon dioxide phase, then 0 calcium carbonate plus carbon dioxide. If calcium carbonate and calcium oxide are chosen as two components, phase calcium carbonate, composition calcium carbonate plus 0 calcium oxide. A phase is calcium oxide, then composition 0 calcium carbonate plus calcium oxide. Phase carbon dioxide, then composition calcium carbonate minus calcium oxide. Now next is the degree of freedom. The degree of freedom of a system is defined as the number of independent variables such as temperature, pressure and concentration which must be specified in order to define the system completely. Now consider a system consisting of pure gas, say A. It is evidently a one component, one phase system. The two variables required to be specified will be temperature and pressure. The composition will remain invariably 100%. The degree of freedom will be 2, that is, the system will be bivariant. Consider now a one component system having two phases. The example is furnished by water in equilibrium with its vapor. The system will have only one degree of freedom because at a given temperature, the equilibrium vapor pressure of water can have only one fixed value. Thus, if temperature is specified, pressure becomes known automatically and vice versa. We have to mention only one variable, either temperature or pressure. The system is therefore monovariant. As you can see this. Finally, consider a one component system having three phases. The example is furnished by ice, liquid, water and vapor coexisting at the freezing point of water. The system will have no degree of freedom. The reason is that these three phases can coexist only at one particular temperature under one particular pressure. The mere statement that these three phases coexist defines the system completely. The system therefore is said to be non-variant or invariant. So a true equilibrium is said to exist in a system under a given set of conditions when the same state can be realized from either direction by following any possible procedure. Now we come to the phase rule. The phase rule states that provided the equilibrium in a heterogeneous system is not influenced by gravity or by electrical or magnetic forces, the number of degrees of freedom F of the system is related to the number of components and number of phases existing at equilibrium with one another by the equation F is equal to C minus P plus 2. Now we come to the one component system. Since the minimum number of phases in any system is 1, it is evident from the phase rule equation that for a one component system, the maximum number of degrees of freedom can only be 2. F is equal to C minus P plus 2, component 1, phase 1, so degree of freedom comes out to be 2. The system is thus bivariant. It can be completely defined by specifying two variables. The two variables are temperature and pressure. The composition or concentration remains invariably 100% because there is only one component. If a one component system has two phases in contact with each other, the, the degree of freedom will be 1. F is equal to C minus P plus 2. One component system, phases are 2, so the degree of freedom comes out to be 1. The system is then said to be monovariant. It can be completely defined by specifying only one variable, either temperature or pressure. If temperature is fixed, pressure of the system is fixed automatically, and vice versa. Thus, the system consisting of a liquid in contact with its vapor, H2O liquid gives H2O gas, is monovariant. If temperature is fixed, the pressure of the vapor is fixed automatically. This is because at each temperature there can be one and only one vapor pressure. If a one component system has three phases in contact with one another, the degree of freedom will be 0. F is equal to C minus P plus 2, component 1, phase is 3. The system is said to be invariant. Degree of freedom here comes out to be 0. You can see it in this picture. It is evident that in one component system, more than three phases cannot coexist in true equilibrium. So, for a one component system having three phases, the degree of freedom comes out to be 0. So, in the next lecture, we shall study the water system, discussion of some important heterogeneous system from the standpoint of the phase rule. We shall study the water system. Thank you.